If you're a DIY dude, like a self-taught home welder or home fabricator, and you are dreaming of building something ambitious one day, like a tray for a 4x4 ute, or maybe not even that ambitious, maybe a workbench or just shelves or a barbecue, or it doesn't matter, but if you're that dude, it strikes me that you probably don't think hard enough about the strength of welds and how that should integrate into the great balancing act of welding, which is to make something strong enough without distorting the crap out of it. Because the more you weld, the more you open that door to distortion. And if you don't weld enough, the thing you build isn't going to be strong enough. And on the spectrum of good and bad, generally down here at bad, both of those options. You turn your job into a pretzel, that's bad. Not strong enough, that's bad. Where is the sweet spot? So you give me the next few minutes and I will show you how to crack that kooky code for simple jobs, okay? Like ghetto engineering in the shed jobs. I'll make you better at it inside 15 minutes. The thing I notice about home welders is they get the bits for their job, whatever they're building, all the cut bits of steel, they're all there, and then they assemble them somehow on the garage floor, or if they're lucky, on a proper fabrication surface, which often makes it a little easier. And then they just do a bit of beard stroking and go, oh, I think I'll weld it enough. That's kind of the end of rational thought when it comes to, is it strong enough? Because the balancing act is important. If you weld it too much, it's going to be a pretzel. If you don't weld it enough, it's not going to be strong enough. They're both bad. So I'm doing this little welding job at the moment, and I'm going through that balancing act now, just running through a few simple calculations in my head just to make sure and sanity check myself that what I produce is going to be strong enough. And you can do this when you just building something small, or you're building a tray, or you're building some shelves, whatever. It's really simple. You just need two things. You need to know how strong is the filler material, and that's staring you in the face, even though it's kind of hidden in plain sight, because we'll get into the because in a minute. But you need to know how strong is the filler material, and then you need to know what loads does the thing you are building have to withstand. Pro tip on this: do not use this advice to build a crane or to build something that lives depend on. Don't make jack stands if you're not a proper welder or you don't know anything about design and calculating stress and strain and all of that stuff. Just build simple stuff that doesn't really matter, okay? This is really important. Like if you're a Boilermaker welder or something, you could probably whip up a crane without an engineer, and if you're an engineer, you could probably whip up a crane with decent welds in it, not as good as the Boilermaker engineer. But, you know, if you're not on that spectrum, don't do shit where lives are in the balance. If lives are in the balance, pay a certified welder to do it and pay a designer to make sure that the stuff that you select is all going to be strong enough and not just fold up like a piano freaking accordion. That'd be nice. Okay, so here's the thing I'm building. It's kind of simple. One part of it is I just have to weld this piece of plate here with weld prep countersink sort of on it onto this piece of M24 threaded rod, which is a very simple job, but I want to make sure it's strong enough to withstand the loads that will be imposed, which are basically a product of this nut's not going to be here. I'm just jigging it up with the nut so that it goes on square, right? So the nut's gone. There's going to be some weights here, and they're going to accelerate it probably, I don't know, 2 or 3 Gs. So there's probably going to be not more than 10 kilos of mass, and it's going to accelerate at 2 or 3 Gs, so we're talking about 30 kilos of force. And then what I do in my head is I say, well, we'll put a factor of safety of 10 on top of that. So we'll make it strong enough to withstand 300 kilos of load safely all day long for 100 years kind of thing. So then we've got design intention, like what load do we have to endure? We got that on one side, right? And then what you need to know is, well, how strong is the material? And The material is simpler than you think, but also a little complex because the manufacturers of all welding filler material want you to think that theirs is somehow special. So they give them whatever name the marketing department can dream up, like Hypermeg. Who doesn't want Hypermeg? Because E71 or E70S6, whatever it is, just not as sexy as frickin' Hypermeg. You know, even with no-name stuff, they try hard. You know, you've got Magmate instead of E71 T11 or whatever it is, okay? And in the stick welding domain, same thing. BOC, Smooth Arc 13. Sounds better than 6013, right? They're all doing it, right? They all do it, and it's completely shameless. They want you to think that their shit is somehow special, when really it's all just designed to a standard. Satin Craft 13. The 13 matters, okay? If you go to Bunnings and you buy something with a name like that with 13 on it, it means 6013 or E6013, same thing. Remember the 60 because that's what we're going to use, okay? Now, your welding wire is notionally 70 or 71. 70 for gas-shielded MIG wire generally, and 71 for self-shielded flux core, okay? The 70 and the 71 are the numbers that we give a crap about here. Now, incidentally, in Australia, if you go to Bunnings, you'll see something with 13 on it in the welding rod domain, and that'll mean 6013 generally. If you're in America, you're much more a 7018 society. But once again, the 70 is what matters. 7018 is a really sexy rod to use, actually, if you stick weld, because it freezes slow and it makes you look 25% better as a welder than you actually are. So that's something to remember, although it can be hard to restart if you only use like half a rod and you've got to get it restarted because the flux caps the other end. But anywho, it doesn't really matter. Let's go with the lowest one, which is 60. And that's a happy coincidence because 60 is an easy number to do mental arithmetic with, and you need to do that here, okay? The 60 means 60,000 psi of ultimate tensile strength for the material. And before you start bleeding from the ears, this really isn't that hard. It's not, okay? Not in the engineering ghetto, which we're about to descend into now, right into the basement of ghetto engineering, okay? Imperial is much easier to use here than metric because metric would be in megapascals, and a megapascal is 1 Newton per square millimetre, which is just, what's a Newton? And too hard, right? We're going to use PSI because the weakest material you can use is 6013 rod, which will have an ultimate tensile strength of 60,000 PSI. Stick with me here. If we run a bead of weld that is 1 inch long, okay, 25 millimetres, but 1 inch because we're working in imperial. And PSI is pounds per square inch, so we need to work in inches. And we make it 1/8 of an inch cross-sectional area, okay? Cross-sectional width, minimum width of the bead, 1/8 of an inch, which is about 3 millimetres, like 3.2. Who's counting? Ghetto engineering, the 0.2 doesn't count, okay? So we've got 1 inch, and the thickness of the bead is 1/8 of an inch. That's 1/8 of a square inch if we run a 1 inch bead. Are you with me on this so far? Let's divide 60,000 by 8, which is really easy because you just halve it and halve it and halve it. So you get 30,000, 15,000, 7,500 pounds of ultimate tensile strength, okay, if you run that 1 inch bead. Now, you don't want to be anywhere near that. Okay, you don't want to be anywhere near it. So let's give that a factor of safety of 10. And let's say instead of 7,500 pounds, we're only going to go as high as 750 pounds. But let's call it 770 because then we can convert back to kilos, all right? 770 pounds would be 350 kilos of safe working load for every inch of weld we do, every 25 millimetres. that's 1/8 of an inch. That's a pretty thin weld bead, okay? 750 kilograms of safe working load. Or if you want to think about it like this, if you're putting on a slightly thicker bead and it's 1/4 of an inch thick or 6 millimeters, then that would be 700 kilos for every inch of weld. Then all you have to do is you have to marry these two things up. The strength of the material over here and the amount of weld you need to restrain the maximum design load with a factor of safety on it. So let's say that I need to restrain 300 kilos by welding this onto here. That's easy to figure out too, okay? There's an even better example, right? Because in the context of doing this project, here's a piece of pipe. It's 33.7 millimeters in diameter. I've knurled it. I hope you can see that. So they're just hand grips. And then I've got this nut here that's actually going to carry the piece of threaded rod. And I've just done a little bit of quick lathe work on it. I've put this spigot on the end of it so that it locates easily in here, and that'll make it easy to jig up. And you can see, I hope, that I've done a weld prep on the side, on the end of this piece of pipe, and also on the end of this nut, so I can get a lot of molten metal right down there into the guts of it. And this tube is 3.2 millimeters wall thickness, okay? 33.7 in diameter. Now let's do some ghetto mathematics on that, shall we? It's about 33 millimeters in diameter, and the circumference therefore is pi times the diameter, and pi's about 3 in the ghetto. 3 times 33 is about 100, which is 4 frickin' inches in bananas, as Curtis would say from Cutting Edge Engineering, okay? So the amount of weld that's going in this joint here, trying not to break any expensive cinematography shit or nudge the microphone. So I'm going to put a bead of weld in there, and I'm going to say it's a full penetration weld that goes all 3.2 millimeters into the prepared end of this pipe and all the way around. So it's going to be 4 inches long and 1/8 of an inch minimum thickness. So 4 times 1/8 is half a square inch, isn't it? Or another way of looking at it is we got our 4 inches of our thin bead, and every inch can take 350 kilograms. So I'm going to have 4 of them, so that's times 2 and times 2. So that's 350 times 2 is 700 kilograms, times 2 is 1,400 kilograms. And even with a factor of safety of 10 on the design load, I need it to restrain 300 kilograms. Therefore, I'm way over. Safe as houses, dude. And there's not much distortion problem with a project of this nature. Distortion is a problem in other areas, though. And what I'm trying to do is open your mind to the point of view that you can do calculations like this for things that are stressed simply. So I might do an example like that for you now that involves something you might be able to relate to. We used exactly the same process for designing a workbench. It's really simple and really common to design a workbench using this shit, right? It's 2-inch square steel section, 3.2 millimeters thick, right? So 50 by 50 by 3.2, or 2-inch square by 1/8 wall thickness. That's what this is, kind of thing, okay? And because we're not numpties, we might use this only for the legs. We might use a different thing to support the top of the table. We might use some of this flat bar, you know, this 50 by 12 flat bar, because it'll be really stiff, much stiffer than just a piece of 2-inch tube going across here. So we'll put that in like that, and we'll weld around it. But we'll only weld all the way up and all the way down on the vertical corners, all right? So that's 2 inches on one side and 2 inches on the other side of fillet weld. That's 4 inches of fillet weld, and let's say it's 1/8 of an inch thick as well. It's kind of the same as welding around that round pipe, because same amount of weld, okay? That means that each one of these corners here, each one of these joints, when there is just mass pushing down this way on the rail that holds up the deck of the workbench, right? When there is load on this pushing down like this, it's got 4 inches of weld. And we said earlier that 4 inches of weld, if it's only 1/8 of an inch thick, is good for 1,400 kilos of safe working load. There's 4 legs on a bench, right? And that means that if we weld it that way and distribute the load evenly on the bench, 1,400, 1,400, 1,400 and 1,400, one per leg, that's 5,600 kilos of load restraint, safe load restraint. And I'd suggest that if you build a bench like that and you put, I don't know, whatever that is equivalent to, like 2 and a bit Hiluxes sort of thing, evenly distributed around the bench, then the welds aren't going to fail, but the bench will fail, right? The rails will fail by bending, and then the legs might fail, depending on how they're braced, by lateral buckling or something, but you're not going to break the welds, even with that load, right? But no one's going to put 2.5 freaking Hiluxes on a workbench. You know what I mean? So that is massive overkill as well. Now, where this really matters is in situations where punters massively overweld the thing that they're building. And I'll give you an example of that, right? If you're using that tube I just threw on the floor there as a rail to support a welding table that you're building, and say you're using, you're putting slats over the top of it with this flat bar, although you probably use 100 by 12, not 50 by 12. It doesn't matter. Anyway, and you're putting a 25 millimetre gap in between each one of them. And then that's like 125 millimetres worth of width for every slat gap iteration. And you've probably got, I don't know, 10 or 12 of them. So there's 12 slats on your bench, let's say, and you're going to weld them just across the top of the tube on both sides of the slat. So if this is your tube sitting there like that, you're going to weld 2 inches here and 2 inches there on the tube, and you're going to do that 12 times. So there's going to be 24 beads of weld that are 2 inches long going across the tube that you're making, that you're supporting the whole bench on. And the problem with that is that's 4 freaking feet. That's like 48 inches of weld only on one side of, or one face of the square tube, right? It's going to bend it like a freaking pretzel. It's going to turn it into an inverted Sydney Harbour Bridge. And you don't need that amount of restraint for the slats. You're going to overweld it to buggery if you weld 2 inches here and 2 inches there, and you do that 12 times for every slat, okay? To avoid bending the support rail of your workbench, the best thing to do would be not build it out of square tube, build it out of something with a section like that, like much harder to bend. And the other thing to do is just weld it less, like weld it 1 inch on each side, which just halves the amount of heat input into the square tube if that's what you decide to use. And I use that as an example because every welding bench I see people make on YouTube is made out of 2 inch by 2 inch square tube. They just buy a shit ton of that and they support the slats with horizontal members that are 2 inches by 2 inches, which is just the shittest engineering choice. Use different material for the the beam type supports on the tabletop than you do for the legs because they're doing different freaking functions, for God's sake. I'd be using like 100 by 10 sort of section of flat bar to hold up the welding table, and I'd be putting, maybe 3 of them across, something like that. Much more rigid, and only welding a bit, like 3/4 of an inch, like 16 millimeters or whatever that is, 20 millimeters, would be fine. It'd be absolutely fine. 18 it is, I think. Yeah, anyway, it's 19.2. Much smaller amount of welding will be fine because every inch of weld you do has got 100 and whatever we said, 300 kilograms of safe working restraint, okay? And you don't need 600 kilos or 1,200 kilos if you weld the full 2 inches on each side. You don't need that much just to hold a slat onto a piece of square tube. That's ridiculous. And you turn your welding bench into a freaking pretzel. So what I've hoped to do with this video, because I just did these sanity checks for myself, is just to say that, you know, instead of just using strange Jedi mental powers to figure out how much weld to put on simple projects so that you get that balance right, you can actually just do a bit of thought about it. And if you just remember that one rule, which is 1 inch of weld is going to be at least 300 kilograms of safe working load when it's loaded in a simple way. So if you're joining two things together like this and you're trying to pull them apart or shear them off, you can count on the 300 kilos. If you weld something like this to something like that and then you bend it because it's cantilevered, that's kind of different, and you don't want to use the same analysis for that. And that is actually a little bit complex and above the pay grade of the average ghetto engineer, and in fact it would probably just be better for the ghetto engineer, I think, to gusset the crap out of that and brace it that way and make it strong enough. But that analysis with the 300 kilos of safe restraint for every inch of weld that's 1/8 of an inch thick, that's only good for simple sort of tensile loads or shearing loads of the joint. The minute you start bending it, you just, all bets are off, and you best not consider it in that way. But anyway, simple fabrication hack that can really lift your welding game, and the less you weld, the less you have to grind, the less you have to scratch your frickin' head wondering how you're going to get that bend out of that thing that you just over-welded. And if that happens for you and you don't bend as many things and they still don't all fall down, my work here is absolutely done. So thank you very much for watching.